Welcome back, everybody, and welcome to a new session on machine learning and the Erasmus Plus course. So today we will try to wrap up what we have denoted as resampling methods and the bias-variance trade-off. And if you go into the weekly material which we have and take a look at it, we have mainly been dealing with this session 4 topic, resampling methods and the bias-variance trade-off. And last week, if we just want to refresh a little bit of what we did last week, we actually had we went for a quick reminder on ridge and lasso regression, and we looked at the statistical interpretation of these methods in terms of Bayes' theorem. Now, this is something which we will not use that much in this course. However, many of the statistical concepts are things which we end up using again and again. So one of the problems with many of the bachelor degrees which we have in physics is that often we teach statistics in a somewhat incoherent way. So some of you may have taken a 1 semester or 2 semester course in statistics and probability theory, but often in many of the physics bachelor degrees, the way we teach statistics is a little bit scattered, which means that some of you may not be too familiar with these concepts, but hopefully the way we've been using them is something which is not too difficult. The statistical data analysis is something which is always under the hood in machine learning, even though the traditional way we do machine learning is an approach where we are mostly interested in fitting data and finding a function which we can use to make predictions and perhaps find some correlations in the data set. However, the statistical data analysis is something which has become more and more important in the last years, and you will often see that this kind of traditional way of approaching machine learning is gradually being replaced with an approach where we want both to make predictions and find correlations in the data sets and the functions which we have fitted, but we also want to estimate the errors, which means we need a probability distribution which describes the data. And we would also like to understand causations. What is the probability of getting A given an input B, for instance? And these were the things which we discussed last week. So let me just quickly remind you of some of the things which we discussed besides a mathematical analysis of ridge and lasso regression. So let me just skip through that one, and because that was a material which came from the weeks before. But let me quickly remind you of some of the statistical assumptions which are made about the functions which we have. So typically, when we deal with a regression problem, whether we're dealing with deep learning methods or we're dealing with standard regression methods or what we might call the pre-deep learning revolution methods like support vector machines, lasso ridge regression, and many other ones, is that we assume that the output which we want to describe is given by a non-stochastic continuous functions. So we often assume that the x's here are not random variables, they're well determined. So if you run an experiment, we often have a very good control over the experimental input, and we assume that there is not much uncertainty there. And we treat them normally as non-stochastic variables. But then there is a noise which we often model with a Gaussian distribution, often centered with a mean equal to 0 and with a standard deviation sigma squared. And then we produce a model. When we then calculate the expectation values, since the expectation value of this epsilon is 0, we have defined the mean value to be 0, then the expectation value of y here is now given by these variables, where the x of I are the given matrix elements in a specific row, which then multiply the vector beta. So this asterisk here indicates that we have a summation over all the rows, the columns of the design matrix X. And we can also calculate the variance. And this is often led to assume that we can take y to be normally distributed. And that was one of the approaches we used in order to derive the expectation values and the probability distributions for y. And we could also derive, based on a probability distribution, we could derive the standard ordinary least squares equation. Similarly, we can do the same for beta. And one of the reasons why there is, you will find linear regression with ridge and ordinary least squares in basically every textbook on machine learning, is that they provide analytical answers to specific expectation values, like the expectation value of the parameter beta, and similarly the expectation value for the variance of the parameters beta. And this makes it very useful in order to gain some deeper insight about what these methods are actually doing. And when we come to deep learning, it's often much more difficult to actually obtain such expressions. Then we went through the derivation of ordinary least squares with a probability distribution. So I won't repeat these things. I just wanted to give you a quick review. And we introduced Bayes' theorem, which gives us a relation between if we scroll down a little bit, it gives us a relation between what we normally call a conditional probability times a prior, or this likelihood here, and there is a normalization constant. So you would read this, a probability of x given y can then be written out as the probability of y given x multiplied with a probability of just x, and this is divided by a normalization constant. And this can be used then to derive ridge and lasso regression. If we assume that the parameter beta, if that replaces x here, the parameter beta is given by a Gaussian distribution with zero mean value, we get ridge regression. And if we have a probability distribution with a Laplace distribution for the betas, then we get lasso regression. So these are ways by which we can interpret the lasso and ridge approximations to the cost function. And keep in mind now that when we look at these different cost functions, they are actually functions which we can decide upon the shape of. And normally we would start with something, if we're dealing with a regression problem, with something like the mean squared error. But then we can add this shrinkage term or regularization terms, as we've been calling them, which give us extra flexibility with parameters which we can fit. Now, the topic which we are going to look more at today again is the topic which deals with resampling techniques. So I'm going to switch back to the Jupyter notebook, and this is basically where we ended last week, and we ended with a discussion of the bootstrap method. And we started to discuss the so-called bias-variance trade-off. Now, as a quick reminder, the reason why we deal with resampling techniques is that normally we don't have that much data. And this is a cheap way of generating new data. And the whole idea behind these methods is that we would like to produce new data based on the data we have by randomly reshuffling. And by doing that, we would then be calculating the expectation values, like the mean squared error, again and again. And we would then take the averages of these mean squared errors. The hope then is that we get a better estimate of the mean squared errors, for instance, and other expectation values. So there are two widely used methods in the machine learning community, and one is more used than the other one because when we have a certain amount of data, it can actually be numerically cheaper than the other one. So one method is the bootstrap method, which, as we discussed last time, is you reshuffling your data set randomly and then picking randomly the data, the given data points. And that is a selection with replacement, which means that you can pick the same data entry again. And then you would fit a model with that. And then that describes one data set. Then you would reshuffle again and pick randomly new data points, which means again that you can pick the same data set. And that would be your new data set, and you would calculate expectation values again. And then you would continue this a given number of times, collect the variables you have, and then take the average of all these expectation values. Now, the other method is cross-validation, and we are going to discuss that a little bit more in detail today. But then we need also to discuss the so-called bias-variance trade-off. And that is a quantity which is often used to give or provide a kind of measure when you start overfitting. And overfitting means simply that if we're dealing with a fitting case, like a linear regression problem, what we end up with doing then is that we would have a mean squared error for the training set, which starts deviating from the mean squared error from the test set. So let's look at these things again on the whiteboard, and then slowly remind ourselves about the bootstrap method. And then we are going to discuss the bias variance trade-off and derive the equations which we then can compute. And when we are done with that, we are going to move on to cross-validation, which is the method of choice in many of these applications. But let's switch to the whiteboard here. So ideally, if we now are looking at a regression case, so let's use that as an example, because things will change a little bit when we move into classification problems. But let's now look at us fitting a function. So we are using, for instance, ordinary least squares, or we could use ridge, or we could use support vector machines, we could use random forests and other of these standard pre-deep learning methods, or we could use a neural network. Now, what we have then is typically we would use the mean squared error as a kind of measure for the quality of the model we have fitted as a test of the model Y. So we have a model Y tilde, and that means that the mean squared error, and this does not need to be the cost function. When we do ordinary least squares, that is the cost function. But if we do lasso, we would have an additional optimization parameter. But in principle, irrespective of method, we would then have mathematical functions which we use to assess the quality of the model. So this is just one way of testing the quality of the model. We have the R2 score. We could calculate the absolute error. We could calculate the log absolute error and many, many other quantities. But the mean squared error is the most common one. And the mean squared error is also the one which is used in this analysis of the so-called bias variance trade-off. Now, if we now look at the calculations we would do then, if we make a fit of the data and compute the mean squared error as a function of the complexity of the model. So if we're dealing with a polynomial fit, this would be the polynomial degree, which would, with higher degree, we would label that as a higher complexity. So this is the complexity of the model. And when we now perform a calculation here of the mean squared error, we would get something like this for the training. If we do this once, so this would be train. And then what we would often see then is that as we increase the complexity of the model, the test mean squared error starts increasing. And that is a sign of overfitting. So we would always see that the mean squared error for training is something which will become smaller and smaller as we increase the complexity, because we get a better and better fit of the model. But then when we apply this to some data which were not included in the testing, then we can actually fail totally. So just to give you an example again, suppose now that we had a data set where we have data which look like this. And then I'm going to mark some in red. So suppose now we make a fit where we fit perfectly these points here with a function which looks like this. Now, when we then want to test this against some data which were not included in the model. So that means the data which you see here, this point, and that point, and that point, you will see then that we are going to fail quite a lot. But if we, on the other hand, if we had made a fit with a model which was a little bit worse, like this one, then perhaps we would get a smaller mean squared error because we're not forcing the training set to go precisely through all the data points. Now, if we now look at the function which you see here, so one of the ideas behind these resampling techniques is that you are not going to calculate this function here just once, but we are going to try to produce new data in an artificial way. Now, in principle, many of the examples you see in the slides here are so simple that we could actually, and you will see examples of that, we can produce new data sets continuously, because essentially what we are doing is to fit a polynomial. However, as we have been discussing many times, what is the actual situation is that the data you have are the data you have. If you run an experiment, it's very unlikely that you will get more beam time to rerun the experiment just because you would need some extra data points. So when you then perform the statistical analysis, and essentially all these methods, as you will also see, are data greedy. The more data you have, the better the fit. Now, however, if you have a limited set of data, what we try to use then are resampling techniques. So a typical situation which you will see then is that the mean squared error, when you calculate that one, for both test and training, you will often have something which produces a band of values. And the thick red line which you see here is meant to represent some kind of average of all the possible calculations you've done. So you would then see a band like this one of values, and you would find a set of mean squared errors which normally lie within that specific band. And you can think of that as many resamplings of your data. And then you would see the same for the training case. Often the training, however, gives a narrow band when you make the complexity of the model larger. But in essence, what you will see is something similar like the one you will see for the test case. So this would be a band of data. And if you just run your calculation once, you may not be sure which one is the one you would like to present to your colleagues. So often you do then resampling. So when you do the resampling, that means that you would perform a calculation of the final MSE, and suppose we're doing that for test. You would do that B times by resampling your data. So you would sum from 1 up to B, and for each one of these, MSE test, and we're going to put a subscript I here to indicate that we are performing a specific experiment. And you would also do the same thing with the training MSE and other observables, or not exactly observables, but expectation values. So you would repeat the same type of calculation here, and you could present those data, but normally what people present are the results for the test data, because the test data are those which say something about whether we are overfitting or not. So this means that we need to find statistical methods which are mathematically sound and at the same time allow us to resample in a numerical efficient way. Now, the bootstrap method, when it was proposed as just a very simple way to reshuffle your data. And then later it has been proven mathematically that this method actually for independent and identically distributed events should approach the correct expectation values, which you would have in the infinite limit. So these are things which we can then use in trying to find a best possible estimate for these quantities like the mean squared error. So if you now look at the bootstrap method, just to remind you of that. So we would have a data set D, So let's just label this with the x's. So we have an x0, x1, up to some xn minus 1. This is the original data set. This is the one we have been given, and this is the one we want to train our model with. Then what you would typically do then is to have a loop for I equal 1 to this b, the number of resamplings which you're doing. Then you would reshuffle d. So you produce now a d of I, and this is something we are going to label with an x0 star, x1 star, up to xn. So we reshuffle the data and pick randomly. So we reshuffle d and pick randomly n entries with replacement, which means that we can actually select the same data point twice or more than twice. When we do that, we just calculate. When we've done this, then we would calculate different expectation values, like the mean squared error. Could be the mean value, it could be the variance, etc., etc. So we would then have an end loop here, and then at the end, calculate final averages. So the bootstrap method is extremely simple to use, and it's very simple to implement. Now, we are going to look at examples of these, but before we do that, we are going to say something about the bias-variance trade-off. Before we talk about the bias-variance trade-off, last week, what we showed is that this method here gives what the central limit theorem says about, for example, the variance of a Gaussian distribution. So last week, what we did was to produce a data set with something like 10,000 data points. And then we reshuffled randomly these 10,000 data points a given number of times. And actually, we did it 10,000 times without producing a new data set, but just resampling, reshuffling randomly, and then picking the new data points with replacement. And when we did that, we saw that the bootstrap method actually gave us what the central limit theorem says about the standard deviation and the variance. So I will just repeat this, but before we do that and look at these examples, I wanted to say something about the bias-variance trade-off. Because this is used as a measure of overfitting and underfitting. Now, the application here, or the derivation, is done within the context of the mean squared error, because it's very easy to derive this using the mean squared error. When you're dealing with classification problems, you would not use the mean squared error, but you would have something like the classification error. And that's something which makes it a little bit more difficult to actually set it up here. Okay, so let's now look at the definition of the mean squared error. If we have the exact probability distribution. So if somebody gives you the exact probability distribution, this would now simply be given by an integral over p of x. And then I would have a y, which depends on x, minus a y tilde squared of d of x. Now, when you now rewrite this, this is going to be given, when we look at the different expressions, as the expectation value of, when we just write it out, of y squared minus 2 times the expectation value of y tilde plus the expectation value of y tilde squared. And just let me quickly remind you of this notation which we have here. If I take the moment of a quantity like y of n, this is the same as the integral in case we have a continuous distribution of y, and we are assuming that y has some dependency on x. of d of x. So this is the basic definition of this expectation value for the continuous case. If we don't have a continuous case, this is simply the sum over all the possible events. So this is x defined by the domain of events. So here we would have a sum over I from 1 up to a given set of events, and where x of I belongs to the set of events, and we would have a p x of I, and then we would have a y of n as a function of x of I. That is for the discrete probability distribution. Now, if you look at this function here, if you now want to redefine things, we're going to simply redefine it a little bit. So if I look at this y tilde squared, which we have in the expression here, this one, this is something which I can simply rewrite as the variance of y tilde plus the expectation value of y tilde squared. So this is just a standard expression for the variance. If I then look at the expectation value of this y squared, what we are going to bring back now is that y of x is assumed to be a function of f of x plus this noise epsilon. So that's a basic assumption we are making about the data. When we are going to move into logistic regression, which we start with next week, then this f of x is going to be replaced with a probability, because a probability is a better quantity to use for classification problems, because then we would often have discrete events like true, false, 0, 1, etc. Whereas now this f of x is assumed to be a continuous function. So what we are going to do now is to actually look at the expression for y squared, which we have up here, this y squared here. So what comes here is just a manipulation and rewrite of the expression for the mean squared error in terms of two new terms, one which we will call the bias, and another term which we will call the variance of the model itself. And this is these are two terms which are extremely useful when we want to study the onset of overfitting, but also underfitting. So we would then rewrite this in terms of f plus epsilon squared. So let's now write it out. And what we would have then is the following, if you had time to write it down. So let's just wait a little bit so everybody has that time to write it down. So let's now write it out. So we have an E, and then we have an F squared plus 2 of F times epsilon plus E times epsilon squared. So now we're just writing out this expression here. Now, remember now again that F is a non-stochastic function. So that means that the probability distribution, which we have at hand, does not affect f of x. So that means that if you look at this expression here, so with the expectation value of f, or given moment of that one, is going to be given by an integral over z over some domain. We have a p of z, but then f does not depend on this probability distribution. So f depends on some variable x, and the probability distribution now does not affect this variable f of x. So that means that this is simply just f of x, and we have assumed that the p of z, the probability distribution which we are having at hand, is normalized to 1. So that means that the first term which we have here, this one, is something which we just can write out as f of squared. And then we have plus 2 And F is again not dependent on the probability distribution which we are studying. And this is now given by epsilon. And we know that epsilon is something which we have defined to be equal to 0, the mean value of epsilon. It's a normal distribution with mean value 0. So what we're left with then is now a term which contains this sigma squared. So that means that what we are left with at the end for that specific term is f squared plus this term sigma squared, because we have assumed that the variance of epsilon, the random noise which we have, is given by this quantity sigma squared, which is actually an unknown quantity. Now, what we need to look at next now is the term which goes like E of f, sorry, not f, but y tilde multiplied with y. So this is the term which we had in here. If we now just remind ourselves for the equation, so it's this specific term. And then at the end, we're going to look at that specific term here. So if you look at this one and we write it out, this is nothing but the expectation value of f plus epsilon multiplied with y tilde. And this is again given by the following expression. So let's just do that. So this will be given by E of f times y tilde plus the expectation value of epsilon times y tilde. Now, the first term is obviously just given by f times the expectation value of y tilde plus the expectation value of y tilde, because they are variables which are assumed to not depend on each other, and then we will have epsilon here. Now, so with y and y tilde and epsilon are independent of each other by assumption. So it means that there are different probability distributions which govern their expectation values, and f is not assumed to depend on the output data, and that probability as well. So when we now bring everything together, what we have then is the following. If you look at these expressions, so bringing everything together, and so now what we have is a term here, which has to be, this term has to be multiplied with 2. I have this term here for this one, which is actually this term here. And then I also know that this term here can then be rewritten in terms of the variance plus this E y squared. So if I collect everything now, what I'm going to get is the following. So I have an f squared minus 2 times the f times the expectation value of y tilde plus sigma squared. And just keep in mind that this one is actually equal to 0. And then I have plus the variance of y tilde plus the expectation value of y tilde squared. So we're just using a rewrite of these expressions here. And what I'm going to do next now is to collect terms. So if you look at the terms you have here, we can actually collect them and rewrite them as the expectation value. And then we have f of minus the expectation value of y and this quantity is squared, like this, plus the variance of the model itself, plus this sigma squared. So this is the formal derivation of these quantities. Now, if you now look at the first expression we have, this is actually something which is called the bias. And this tells us the deviation from the model by the mean value of the data points. Whereas the second term is just a variance in the model itself. And finally, we have this unknown parameter sigma squared. So let's collect all these terms and look a little bit closer at them. So we have an expectation value of f minus the mean value of the model. And this quantity here is the quantity which is called the bias. In a way, you can think of that as a measure of how much we differ from the data we want to, or the function we want to reproduce, and plus this other term, which is the variance of the model. So this is normally called the variance, plus this term sigma squared, which we normally don't have a value for, except if we have made some experiments and we have an estimate for the noise which is being present, then we could actually come with a prediction for this sigma squared. Now, if you now look at this bias, since f is an unknown function, what is normally done now in order to be able to calculate at all, then what we typically do is that we replace in actual calculations, then we replace this f. So this is an approximation which is made, f with the output y. So that means that this bias actually gets approximated with, and since this is an expectation value, and we are replacing the function, the unknown function f, with the data set, and this is simply done in order to be able to perform any calculation at all, then we have a y of I minus the expectation value of the model itself. And this is being squared. So this is a bias. So you can say that it measures a kind of deviation from the mean value which the model provides, and then the data set which we want to produce. So f is unknown. In all actual calculations, we therefore approximate f with the output data itself. Now, one way to understand this is to go back to the image which we looked at last week. And let's take a closer look at that before we move into numerical examples. So you can now think of a case here where you have a target in here. This is the target you want to reproduce. And then you have these different circles. Now, if your model, so let's now say we have a high bias. So the data point which you see here, this one, that's the mean value of your model. Now, if your model deviates a lot, then clearly you are going to get a high bias. This is typically something which happens when you have a model with a low complexity, because a model with low complexity is normally a model which has a worse fit of the data. Now, what you could have is high bias and low variance. And this happens also typically when you have a case with a low complexity model. So a low variance means that the model itself, which you have produced, produces predictions which are close to this mean value. So that's a low variance. You can think of that as a low spread in model prediction. In model prediction. So this is one typical case which you will see when you now analyze your test data. So this is an analysis which is made on the test data. So this analysis, let me just remind that analysis here is made on the test data. These are the data which are being left out from the training. And this is where we actually measure how much the model which we have built up deviates from actual data which were not included in the training. And that tells us something about the quality of the model itself. Another case which we can have is a case of high bias and high variance. And both of these are unwanted, obviously. What we want is both a low bias and a low variance. So we can have a high bias and a high variance. And if we look at this model here, we have the ideal in here, and then we have these different circles which define our target. So if we have a high bias, it means that the data has a mean value here, so it's still a high bias. But if we have a high variance, this is the same as a high spread. So high variance for the model itself means that the predictions we are making with the model can be scattered all over. So the mean value has a position, but then the various predictions are spread all over. So this is a case of high bias and high variance. And it's normally also, since we have a high variance, it's normally often connected with overfitting. Because with overfitting, you can see now that the predictions are far away from a mean value here. And then we have two other cases, obviously, when we play around with the words we can have a low bias, and we can have a high variance. So high variance is a typical signal of overfitting. So we still have our ideal here, and then we have so we have a low bias, which means that the prediction we make, the mean value of all the predictions for the test data, brings us pretty close to the target. But then we would have a big scatter in the predictions which we make. So that means that we have a high variance. And again, this is a high spread in data. And finally, we have the ideal case, which is both a low bias and low variance, which means that we are close to the target value with the mean value of observations or the predictions we're making. So we have a result where we are here, and then there is a very small spread in the predictions which we make. So this is actually the ideal case here. So before we take a small break, I just wanted to set up how this is going to look like when we now perform an analysis of the test data and the mean squared error. So let's just make a quick plot of it as a function of the complexity of the model. Complexity of model. So this could be a high polynomial degree. And we are just looking at the mean squared error for the test data. And this is the result we get after resampling. So you can think of this having been calculated with a method like the bootstrap. So we are pretty sure that the value we provide for the mean squared error is something we think is reliable after having done a resampling technique. So what we would typically get then is something which goes like this. So this would be the total mean squared error, which can go something like that. So this is our mean squared error for the test result. Now, in the beginning now, what you would see is something which looks like this. So this is a kind of ideal situation. So this is the bias. So that goes down when we increase the complexity of the model, because when we increase the complexity of the model, what happens then is that we are making a better and better fit. So the mean value which we predict for the model is close to the data which we want to reproduce. However, what may happen next is that if we look at the variance, in the beginning, that can be pretty small, and then it starts increasing here, and then it takes over with respect to the bias. So this would then be the variance. And when we have a case with the overfitting, so this what we have here is a case of overfitting. And what happens in overfitting then is that the spread in your prediction becomes larger and larger. And at the end, this variance of the model itself just becomes extremely large. So this is a typical analysis which you will see in many, many machine learning articles and textbooks. So for the mean squared error, this is straightforward to derive, whereas for other types of class or scores like the classification case, we cannot use this kind of simpler pictures with the mean squared error. We would then have to look at other ways of quantifying the overfitting case. But overall, this is a kind of a picture which we expect to see when we are running machine learning codes. Okay, I went a little bit over time, so let me put the recording on pause here. So before the break, we looked at the bias-variance trade-off, and we found a specific recipe by which we can perform a test when we look at the mean squared error in terms of the variance in the data set which we predict with the model. And in our specific case, what we did was to simply rewrite the expectation value for the mean squared error in terms of this bias parameter and this variance parameter. And in addition, we have this sigma squared, which we not often may be able to quantify properly. So the way we can think of this in a pictorial way is that if we have a high bias, then there is a large deviation from the mean value of the prediction from the model and the data point which we want to reproduce. If we have a high variance, it means that we have a high spread in the model predictions. So the ideal is actually that we would like to have a low bias and a low variance. That's the ideal case. And we want to have a mean value of the model prediction, which is as close as possible to the data we want to reproduce. And at the same time, we want to have as little spread as possible in the model. And a large spread means a large variance. And typically what we end up seeing is that we have a flag for overfitting when this variance grows large as a function of the model complexity. So what we are going to do now is to switch back to the Jupyter Notebook, and we are going to look at the examples. And then at the end of in the second half of this second lecture, we are going to look at the cross-validation method as a way to perform the estimate of the mean squared error based on different ways of resampling the data. So let's take a look at the examples and applications of bootstrapping and the bias variance trade-off. So in the codes which you have for this specific week here, there are examples of resampling techniques. So one of the things we discussed last week was a demonstration that the bootstrap method gives us what the central limit theorem predicts. That means that when we have an expectation value for the variance for one specific sample, and if we perform this many, many times, then we should get a mean squared error, and variance, which has a spread which is given by the original value divided by the square root of m. So this would be the standard deviation, and the variance is just the square of the standard deviation. So we studied these quantities last time, and we are not going to repeat them here, but we are going to look at the bias variance trade-off. So these were the equations which we derived before the break. And there is a code here. If we just scroll down here, there is a code now which we're going to take a closer look at. So this code uses Bootstrap. And in this case, what I've done now is to set up 40 data points, and I do 100 resamplings, which sounds a little bit strange, but let's just do it. Normally, most practitioners, they tend to have less Bootstrap resamplings than they have data sets. And in this case, I am considering a polynomial of degree 14, which is the model I want to reproduce the data set which you see here. So I add some random noise, as you can see here, which is given by a normal distribution. And the function is now a simple one, but with exponential instead of a polynomial. So which means that if I want a polynomial, I should get to very high degrees before I can get a very good description. And then I have a data set X, which is set up between -3 to 3. And my function here is now an e to the minus x squared, another x squared, plus some random noise. And what I'm going to calculate now is the mean squared error, which is this quantity. I calculate the bias, and I calculate the variance using these expressions. Now, before I start looping, I perform now a split in train test. So I have a data set here, which is kept as it is for the rest of the time. Now, one of the things which I do next, so the test set is just kept unchanged. So what I do next now, I use the functionality which you have in scikit-learn, which now runs over polynomial degrees, and it sets up a polynomial of a specific degree. So this is me trying to test the model complexity against the bias and the variance. And here I now make a prediction, which is a prediction array, but then I perform bootstraps. And for every bootstrap, I make a prediction. So for every bootstrap here, I now compute new values for X and Y. And then I train these values with my train, X train and Y train. And you see now that I have X and Y here are now simply given by this resample function, which is included with scikit-learn. And that resamples my X train and Y train. Then, in every case here, what I'm doing next now is simply to take my prediction here, and I make a model fit. And then I have my test, which is given here. And that means that I make a prediction here for every single X and Y here. And that prediction is now based on the test set, which is untouched by the bootstrapping. So for every bootstrap, I resample my training data, both for the input X and for the output Y. I use this functionality here to set up the polynomial degrees. And alternatively, you would have to set up your design matrix again and again. And then I make a prediction. And with that prediction, I'm now calculating the mean squared error only on the test data. So this is my test data minus the prediction. So this is just a calculation of the mean squared error, nothing but that. And I do that for all the data, which all the cases I've done here. So I've actually, since I've done 100 bootstraps, I have 100 predictions. And then I calculate the bias in the same way, and I calculate the variance again. And this is obviously the mean of all the predictions I made. And then I plot them, and let's see what happens when we just run this. And when we run this now, what you're going to see, I think I have to rerun something here. Yeah. So I just need to rerun because I had forgotten to I think I have a let me just look at this one. I think there's something which has sneaked in here. I think there must have been there is a an error here which just came in here. Okay. Yeah, somehow I see what happened here. Sorry for this. There we are. By some strange reason, I mean, there were some copy paste which I just sneaked in here. But when you now look at the different calculations which we are doing now, we do the different polynomial degrees. That calculates the total error. So the bias plus the variance, they should obviously sum up to the total error, because this is just a way of rewriting it. The thing which is interesting for us now is the following. So you see now that first, we will not get this kind of smooth pictures, because this is just a function of discrete degrees of the polynomials. So you will obviously get these lines which are drawn between the different polynomial degrees. And you see now that the error goes down as we increase the polynomial. So on the x-axis, we have the polynomial degree. So that's the model complexity. And then you see also that the bias goes down. But then we reach a region here where we start to overfit. And that is where we start making predictions which are worse than those which we would like to have. And you see now that the variance increases. So this includes this is a flag of overfitting, because the variance represents the spread in the model predictions which we make on the test data. So what you see here is a typical example of an analysis which you can make of the bias-variance trade-off. And typically what you would say then, if you look at these results, you would say now that the model around polynomial degree of 8 and 9 seems to produce the lowest possible error, the lowest bias, and the lowest variance. And when the variance starts increasing, that's a typical signal of us entering a region of overfitting. Now, these results will always depend on the amount of data we have. So if we now have 400 data points and we rerun these calculations, what you will see then is a totally different picture. So everything we do now is something which will depend on the amount of data we have. So this particular case here, you see now an error which is given by the sum of the bias and the sum of the variance, obviously. And this seems to be flattening out for this polynomial degree. So with 400 points and a polynomial of degree 12 and 13, it means that we are actually having a model which has an acceptable error. So the error and the bias are almost on top of each other here. And the variance is still pretty low. If we increase the polynomial degree now, suppose we put this to polynomial degree 30 and just see what happens then, we could still experience that these results will have a very low bias and variance. So this is something which we need to test depending on the amount of data we have and the type of function which we're trying to fit and the model complexity. And you see now in this case, when we have reached a polynomial degree of 23 roughly, we see now that the error is spiking up, so it's increasing. And this would again be a sign for this data set that when we have a polynomial of degree 20, between 20 and higher, we are starting to enter a region of overfitting. So these are typical examples of what you may see when you run the analysis. Now, clearly here, there is something else we need to think of. If you look at the cases which we have here, up to polynomial of degree 15, from a polynomial of degree 10, or even 7, 8, to a polynomial of degree 15, 16, 17, we see now that we have basically a very low variance and a very low bias and a very low error, which means that we could equally well say that, okay, let's stop at polynomial of degree 7, because that produces basically the same set of errors as we have for a polynomial of degree 18 or 17. Now, just keep in mind that if we make a very complex model, often the case is that you want to use this model, this fitting, in some calculations. So if you have a polynomial of degree 6, and that gives roughly the same qualitative good results as a polynomial degree 20, you would use a polynomial degree 6 in your calculations, because that requires much less floating point operations. So when we are summing this up here, what you see now is that this bias-variance trade-off, it summarizes a fundamental tension which you see in machine learning, in particularly supervised learning, between the complexity of a model and the amount of training data which is needed to train it. And since data is often limited, in practice, it is often useful to use a less complex model with higher bias. That is, a model whose asymptotic performance is worse than another model because it's easier to train and less sensitive to sampling noise arising from having a finite sized training set, smaller variance. So this simply tells us that in order to minimize the expected test error, we need to select a statistical learning method that simultaneously achieves a low variance and a low bias. Remember also that the variance is a non-negative quantity, and the squared bias is also non-negative. So we see that the expected test MSE can never lie below the variance of the noise which we have. So the variance, as we said, refers to the amount by which our model would change if we estimated using a different training data set. And since the training data are used to fit the statistical learning method, different training data sets will result in a different estimate. But ideally, the estimate for a model should not vary too much between training sets. However, if a method has a high variance, then small changes in the training data can result in large changes in the model. So this is actually what you have been seeing here. There's another example which I took from scikit-learn, which also illustrates this. So we have the model, we have the true function, which is the orange line, and then we have some samples. And in the case we have a degree 1 polynomial, you see that we have a mean squared error, which is approximately 10 to the minus 1. I take a degree 4, and this is actually a function of degree 4. And these are some samples with noise here. And you see now that the polynomial which I'm fitting is doing a pretty good job. So I have a 10 to the minus 2. But then I have a typical case of overfitting, where now, as you can see, the model is actually going through basically all the data points, which we have the samples. And then you see now that this clearly produces a result with a huge mean squared error of 10 to the 8 when I have a polynomial degree 15. So these are the type of analysis which we often end up making when we're dealing with machine learning. Now, the other method which I wanted to conclude this lecture with, which is more used than standard bootstrap method, is the cross-validation. So let me just try to set up the cross-validation algorithm, because that's also pretty simple. So what I'm going to do now is just to switch back to the whiteboard. So let's do that. So cross-validation is often the method which we would end up using. And it's a method which is pretty simple to implement. So let's just set it up. And scikit-learn has implementations of it, which are pretty easy to set up. It's also easy to make your own code. And I will discuss this code after we've gone through the method itself. So the key topic is then to divide the data in so-called folds. Or you can think of this as slots, so k folds. So suppose we have a data set which looks something like this. And we decide to split this in k equal 5 folds. So let's just split it in here. And what you would do then, in the first case here, 1, you could now set up, so the blue color here is the train data. So blue is training. And then the red one here is my test data. So I would train my model on the blue data. So I've split it in 5 slots. If I have 100 data points, it means that we would have 80 data for training and 20 for test. And you can change this K to larger, smaller numbers. If you just keep one data point for testing, that is an approach which is called leave one out cross-validation. But then you would have to run this for the whole data set. So in total, you have n data points. So with K equal 5, it means that you have 20% for testing. Now, when you've done this training, what you would do then is to calculate the mean squared error for test. And this is example, the test for case 1. Then we have case 2 here. And then we repeat this kind of splitting. But now the training case could be, the test case could be this one. And we have the train data, which are given by these other data slots. And again, what we will do now is to calculate, in this case, the MSE for test, for this case 2 here. And then you can see that it's very easy to figure out what is the next step. The next step is just to reuse one of the other slots, which was used for training, for testing. And in total, we would have 5 different calculations of the mean squared error for test based on this training procedure. So that means that the third case could be something like this. So we could have training here, no, sorry, test here, and then we have these other 4 slots for training. And we would calculate again the mean squared error for test for this case. And now I'm just going to draw the last 4 slots here without the last 2 slots. So let me just put them up. That means that this would be the train case, and this would be the, no, sorry, the test case, and these would be the training cases. And that means that the total mean squared error is now given for test, is now given by 1 over 5, the number of folds, I equal 1 to 5, and then we have this MSE test for I here, like this. Now, the thing is that we don't know how sensitive the results are to the number of folds which we have made. So typically, what you will see is that most practitioners, they tend to have between 5 to 10 folds. If you, as I said, if you just leave one data point for the test case, it means that you would have to run this n-1 times, and this becomes more expensive from a computational point of view. So the whole thing with the cross-validation is a compromise between the accuracy you are interested in and the number of floating point operations you want to spend on this type of calculation. So as you can see here, the method is very straightforward. The only catch, perhaps computational complexity, is you having to split it in different boxes or slots or folds, as they're called, and just keep track of the indices for test and training. And when you have that, which you can, where you can use the functionality of scikit-learn or write your own function, then you can easily then just set up the cross-validation. And the cross-validation is the kind of method of choice in the literature and in most applications in machine learning. So the algorithm, as you can see here, is extremely straightforward. It's not very complicated. And it gives a pretty decent estimate of the mean squared error for the test data. It is obviously going to be different from the one you get from bootstrapping. But normally what you will see when you have lots of data is that these two methods, they tend to approach each other, except that the cross-validation is often a method which involves less floating point operations. So after this, let's try to go back to the Jupyter notebook and look at the actual implementations of these methods. So let's take a closer look here. And there are codes here, so it's often much better to look at codes, as you can see here, for the various values of k. Shuffle the data set randomly, split the data set into k groups, and for each unique group, you decide which group to use as a set for test data. Take the remaining groups as a training data set, fit a model on the training set and evaluate it on a test set, and retain evaluation score and discard the model, and then repeat this till you've gone through all the test sets, and then you summarize the model using the sample of model evaluations or model evaluation scores. So it's pretty straightforward to implement. And you can see now a simple code here for a very simple function. So again, we have this very, very simple vanilla type of data. And in this case, I'm using ridge regression because I also wanted to remind you a little bit about how we implement ridge regression. And in this case, we have 100 data points, and we have random numbers normally distributed for x. And then we have the values for y. Now I'm doing something stupid because this is a second order polynomial, but I'm actually going to fit a sixth order polynomial. So I'm assuming that I don't have any idea of what the data set is, and I just pick a sixth order polynomial. I run through 500 values of lambda, and I let them run from 10 to the minus 3 to 10 to the 5. Now here I have my own code, or rather, what I'm doing now, I'm using the k-fold functionality of scikit-learn. I decide that I want to use 5 folds. And then I run my loop over lambdas. And then having used this functionality here, that tells me where the different training and test indices are going to start from. So I can now set up my x train, my y train, and then I have my x test and y test. I perform the fit here, and I use ridge regression, and then I obtain my test, and then I make my prediction, which is now the mean squared error in my case, as you can see here. So that's just my mean squared error, which I'm setting up. And this is just a simple implementation where I actually now cheated a little bit, and I simply use this way of setting up the training and test indices when I'm splitting the data. And then I take the mean of all the scores which I've calculated, and then produce the final estimated mean squared error. The functionality which you see here is the one which follows scikit-learn. So in this specific case, what I'm using is a function called cross-val score. I transfer ridge as a method. I have my x and my y, and the scoring is the new is a mean squared error. And then I do cross-validation with k-folds, and I have defined the k-folds to be 5. So hopefully scikit-learn's code gives the same result as my own code. And today my code is actually running pretty slow. And you see now that my own code, where I use this fold splitting functionality in scikit-learn, and the one where I just use the full scikit-learn options, you see now that for this polynomial degree of 6, I'm actually getting a mean squared error here for a lambda value slightly larger than 1, which seems to be giving the best result. Now, however, we know that these results will change as a function of the model which I'm putting in. So when I run these calculations, I actually put the model degree to 6, but actually it would be better to put it to 2 here. And let's see what happens then, because then the results will change. So if you look at that one, we're having now a polynomial which is closer. And you see in this specific case, I'm still getting the same with my own code and scikit-learn. And in this case, we actually get a fit here, which has a mean squared error, which is better than the previous one. It doesn't have that dip. And if I take away the random noise in addition, I should get a perfect fit. And if I take away the random noise, I should get a mean squared error, which is 0. And in this case, what we have is actually a case where ordinary least squares is doing a better job. And you see now in this case, both what scikit-learn predicts and my own code, we get basically the same result here for ridge regression. So this is a typical implementation of cross-validation, which you would use in the data analysis. This textbook by Hasty et al., which is linked in the README file, and which I also sent as a link to you, contains an in-depth discussion about these different methods. And there are more examples here on how you can use that. This is a case where I've taken the energy per particle for infinite nuclear matter, and the energy comes in as a function of density. And I'm using pandas here to read in a CSV file, which you can have access to. It's called the EOS CSV. So it's the result of a theoretical calculation here. And here I'm making a fit in terms of a polynomial, which depends on the density. So this goes like the power of the polynomial to degree 1/3. And then I perform a fit of my data. And in this particular case, I'm actually using a ridge regression again, as you can see. And I'm performing a linear fit here. And no, sorry, this is not a no, this is actually a case where I'm just using standard ordinary least squares. So if I'm running this through the different polynomial degrees, what you will see then is that as you increase the complexity of the model, the mean squared error is getting better and better. And if we now look at the case which we had here, but without cross-validation, I'm getting something which looks like this. And you see now that the training gets better and better. But when I have reached a polynomial degree 10, I'm starting to overfit, which is expected, that somehow you will always overfit here. You can repeat this with cross-validation. So that was a case without cross-validation. And we get a test error in this case, which is now basically pretty similar to the one we had before. But you see now that the test error is a little bit higher. So it's in a log scale here. So we're still having a pretty large test error here. So these are typical examples which you can run with cross-validation. So here I'm just using ordinary least squares. And I am using the cross-validation optionality which you have in scikit-learn here. I wanted to say something about the exercises before we end. So these are also exercises which we had last week. So one of the things I wanted you to take a look at is actually the bias-variance trade-off, and take a look at these examples which we have of codes, and try to implement your own application of the bias-variance trade-off, because this is something which we will include in the first project. And try to do that with the bootstrap method, because that's the simplest and most straightforward way to implement the bias-variance trade-off test.